In its most basic form, the principle of conservation of energy means that similar to mass, energy can neither be created nor destroyed. Hence, as we have seen before in our explanation of the control volume approach, for a control volume that is at steady state, the energy flowing into the control volume must be equal to the energy flowing out of the control volume, in order to satisfy the conservation of energy principle. There is, however, a major difference between mass and energy conservation. Mass can only flow into or out of the control volume when carried by the flow through a part of the control surface that is an inlet or an outlet. In other words, mass cannot pass through a solid wall. On the other hand, energy can pass through a solid wall, and hence can flow into or out of the control volume, through any part of the control surface, whether it is an inlet or an outlet, or a solid wall. Consider the shown control volume that has an arbitrary shape. There are three types of energy that can flow through the control volume. The first is flow energy. This is energy that is carried into the control volume by the incoming flow through the control volume's inlets, and out of the control volume by the outgoing flow through the control volume's outlets. It is expressed by the variable E dot. Flow energy cannot penetrate through a solid wall, and it can only enter or exit the control volume through an inlet or outlet when it is being carried by the flow. The next two energy types can flow into or out of the control volume, through any part of the control volume's surface, even if it's not an inlet or outlet. Work energy can be work done by, or on, the control volume, using a mechanical device, such as a shaft that is connected to a propeller, or by a piston. It is expressed by the variable W dot. The third type of energy is heat energy, which can flow into or out of the control volume, due to a temperature difference between the control volume and its surroundings. It is expressed by the variable Q dot. In our current study of the conservation of energy, we will only consider energy flowing into or out of the control volume, while carried by the flow through an inlet or an outlet. We will not consider work or heat energy. Consider the certain mass m of a fluid that is contained in the shown cylinder. We wish to quantify how much energy is contained in that fluid mass. We express the total energy content of the mass m of the fluid by the variable E, which has units of joules. The total energy contained in the mass m is equal to the mass m in kilograms times the energy per unit mass contained within that particular fluid mass, which is written as small e. The energy per unit mass, or small e, has units of joules per kilogram. If we now imagine that the shown cylinder is actually a pipe, through which a fluid is passing, then we can determine the rate at which energy is being carried by that fluid through a given pipe cross-section. The rate at which energy, being carried by the flow, is passing through the pipe, is expressed by the variable E dot, which has units of joules per second, or in other words, what's V dot is equal to the mass flow rate, m dot, which has units of kilograms per second, times the energy per unit mass of the fluid, or small e. In terms of the energy per unit mass content of a certain amount of matter, we can consider 6 types of energy: nuclear energy, molecular bond energy, internal energy, pressure energy, kinetic energy, and potential energy. Potential energy can further be divided into potential energy due to a gravitational field, an electrical field, and a magnetic field. Hence the total energy content per unit mass of a given amount of matter is the sum of all the aforementioned energy per unit mass forms for that particular amount of matter. In our current consideration of this subject, we will neglect any energy type that does not change. Hence, assuming no nuclear or chemical reactions take place, we can neglect nuclear and molecular bond energy. Furthermore, assuming the temperature of the fluid remains constant, we can neglect internal energy. Finally, assuming the fluid is not electrically charged or magnetized, or is not moving within an electric or magnetic field, we can neglect potential energy due to electric and magnetic fields. We are thus left with pressure energy, kinetic energy, and potential energy due to a gravitational field. As we have seen in the previous section, the energy per unit mass equation for a given mass of fluid can be simplified to include only the pressure energy, the kinetic energy, and the potential energy due to gravity. The pressure energy per unit mass contained in a given mass of matter is the energy content in that mass due to it having an internal pressure that is more than that of absolute vacuum. For a fluid at high pressure, one way of converting this energy to potential energy, for example, is by allowing the fluid to expand while lifting a weight against gravity. In this case we relax our usual assumption of the fluid being incompressible to it being nearly incompressible, in order to allow for the fluid to store pressure energy by slightly contracting under the effect of outside pressure. The pressure energy per unit mass is equal to the fluid's internal pressure divided by the density of the fluid. The kinetic energy per unit mass contained in a given mass of matter is the energy content in that mass due to it having a velocity relative to a stationary frame of reference. The kinetic energy per unit mass is equal to half the fluid velocity squared. The potential energy due to gravity per unit mass relative to a reference location is equal to the gravitational acceleration times the height h above that reference location. By substituting the expressions for pressure, kinetic, and potential energies per unit mass, we obtain the shown equation for the total energy per unit mass of a fluid. For all three energy forms, after substituting for the units of the variables and simplifying, we see that we get the usual energy per unit mass units of joules per kilogram. As we have seen before, for a control volume that is at steady state, the conservation of energy principle implies that the total energy that is flowing into the control volume must be equal to the total energy that is flowing out of the control volume. Click on the shown link if you'd like to review that section. In addition to being at steady state, we assume no work or heat are being added to the control volume, and we assume constant density and uniform velocity and pressure at all inlets and outlets. We can then write the conservation of energy equation in terms of only the flow energies into and out of the control volume. Thus the summation of all flow energy going into the control volume must be equal to the summation of all flow energy going out of the control volume. Substituting the equation we got before for the flow energy, capital E dot, is equal to m dot times lowercase e, we get the shown equation. That states that the summation of the mass flow rate times the energy per unit mass at all inlets is equal to the summation of the mass flow rate times the energy per unit mass at all outlets. Click on the shown link if you'd like to review that section on flow energy. We can also substitute the expression we obtained for the energy per unit mass. See that section on energy per unit mass for more information. And thus we obtain the shown expression for the conservation of energy equation for multiple inlets and multiple outlets. We have previously obtained the energy conservation equation for a control volume that is at steady state with multiple inlets and outlets. By assuming the single inlet and a single outlet, we can drop the summation sign from the previous equation. Furthermore, based on the conservation of mass principle, at steady state, the mass flowing into the control volume must be equal to the mass flowing out of it, and hence the mass flow rate can be cancelled out from both sides of the equation. We finally get the shown equation that states that for a control volume at steady state with a single inlet and a single outlet, the pressure divided by the density plus half the velocity squared plus the gravitational acceleration times the height above a given arbitrary reference plane for the inlet must be equal to the same quantity for the outlet. We then get an expression that is known as Bernoulli's equation that states that for uniform steady-state pipe flow with no flow losses or work added, P divided by ρ plus half V squared plus G times H is equal to a constant value everywhere in that pipe.